missed one of the sessions we did. I realized the recording didn't start because I didn't hit the button correctly, but this time it did. Okay, good. So what is this chapter? So this chapter, sessions 50 through 60, is supposed to be about applications of integrals. We've now seen some examples of using the integral to define measure, which is useful for speaking precisely about volumes in higher dimensions. We used it to define new functions via integrals, so like the gamma function, which we defined as a function of x as some integral from 0 to infinity of t to the x minus 1 e to the minus t dt. So we saw that the integral is useful in defining new functions, and then we saw some relationships between those functions, proving some of those identities today. And for this, maybe next 2 or 3 sessions, I want to do some examples of how we use integrals in context in science. So it'll be a little harder. Some of these calculations are like taken directly out of, kind of mid undergraduate program chemistry or physics courses. So like the ideal gas law, the proof of this is something you would see in like a sophomore level chemistry that's a thermodynamics course or a sophomore level stat mech course in physics or something. So don't expect to follow all of the details. It's more of a preview, but you'll see how the pieces fit together and how we use the results of some of these integrals, and in particular volumes of spheres, in this proof, and then we'll do some physics. So this work energy theorem is, it's kindergarten physics. You would even do this in AP Physics C in high school, but it'll be a good application of how the integral is useful, and it'll show us, I think, how conserved quantities are useful in solving problems. So that will be the plan for today. Questions about that before diving in? Ba-doop.
I do not have any questions. I'm curious, like Discord is playing on mute and unmute through your speakers.
I'm just going to say doop. There it is again. I don't know why that's happening, but okay, if there is nothing, I will carry on. So I have a 1-slide review of Stirling's approximation, which you proved yesterday, just because we're going to use it in the ideal gas law. So what did you show? The question you were trying to answer is, when n is very large, can you approximate the factorial in terms of other functions that are easy to differentiate, basically? So remember that the factorial is the same as the gamma function evaluated at an argument shifted by 1. So you can interpret Stirling's approximation as either a formula for the factorial when n is large, or as a formula for the gamma function when n is large. I actually would argue that it's better to interpret it as a formula for the gamma function, because the right side of this equation consists of all functions for which we can plug in any real number, right? You can plug in a fraction, like 3/4 to square root or n to the n or e to the minus n. So the right-hand side works even for non-integers, but the factorial is only defined for integers. So since the right side is defined for all reals, we should really think of this as a formula for the gamma function, because the gamma function is the continuous version of the factorial. So anyway, you prove this using the trapezoid rule and integrating log and setting these approximations equal or something, and then you went into Python to get this root 2 pi, this overall prefactor. So I just wanted to show you a plot to get a sense of how closely these guys agree, because the approximation is very good even when n is only like, 3, right? So what's happening in this plot? So the blue dots are the factorials. So 0 factorial is 1, 1 factorial is 1, 2 factorial is 2, 3 factorial is 6. The blue curve is the actual gamma function, which, as we know, should connect all of the factorial dots, because the gamma function generalizes the factorial to a smooth function. And then this pink curve is Stirling's approximation. The root 2 pi n over e to the n, which you found the other day. And as you can see, Stirling's approximation has some error compared to the gamma function at low values, like this is between 0 and 1. It gets closer between 1 and 2. And then even by 3, these things are very, very close. So for large numbers like 10 to the 23, they're so close that the fractional error is totally negligible. So when n is large, we're going to use the Stirling's approximation just totally without apology. Just going to freely use this because the approximation is so good. And that'll be nice, because if you're doing algebra or calculus, it's much easier to differentiate things that involve exponentials or square roots than factorials or gamma functions, right? You don't want to carry around derivatives of the gamma function in terms of digamma. You don't want to write an ideal gas law that involves the fucking digamma function. It should be nice things. So anyway, that's the philosophy for having this approximation, which we'll see how it's useful. Good. thoughts on this thing, this picture?
I do not have any thoughts. I've taken to not muting myself in between comments because now it's just going to get obscene.
Good, good. I can hear little snickers, which I like, because now I get to hear reactions, because you're not muting yourself. Okay. Alright, so let's prove the ideal gas law. I use the word prove loosely, but I think you should at least see where it comes from, because in like a chemistry course, when I find it very intellectually dishonest when people just write down something like PV equals nRT and tell you this is how gases behave and expect you to believe this without any sort of justification from first principles. On the other hand, I can't actually prove this for you rigorously, because to do so I would have to go through basically the first month of a thermodynamics class and prove all of that stuff, which I'm not going to do. So I'm just going to kind of take a middle path and cite some results, tell you some things that you could prove in a thermodynamics class, and then sketch the calculation for you. So,
Why not go through the entire class?
well, do you want to take a 1 month break from calculus to do thermodynamics? I mean, we could, or we could do that after calc if you want. I mean, I'm more than happy.
Both of those sound like terrible ideas.
Yeah, I mean, I'm not sure if you want to do thermo just yet, but I don't know, maybe someday. We'll have to decide what we do, if anything, once we finish calc, if you want to learn more stuff. So, doing more physics is one option. But anyway, for today,
String theory.
I could do that. There's a very nice undergraduate string theory book by Spivak that we could do. But good. Okay, so let me give you a caricature of what you would do in the beginning of a thermo class in physics or chemistry. So the first thing you normally learn in a class like this is something called the Microcanonical Ensemble, which is a very fancy word for something which is actually much simpler. So all this is you consider you have some box. So we're going to have some box, and let's just do 3 dimensions for now. So some, 3-dimensional box that later the actual dimensions of this will become important. So let's say it has like some L in the X direction, L in the Y direction, L in the Z direction. So there's some dimensions to this box, and we're going to say the volume, which of course we know is just the product of these 3. Volume is Lx, Ly, Lz, or whatever. Alright, fine, so you have some box, and there's n gas particles inside. So 1, 2, 3, 4, 5, 6, ... n. Imagine the other 6 times 10 to the 23rd, or whatever of these. So imagine there's a large number, n gas particles in a box. Eventually we're going to want to get the ideal gas law for these particles in a box, but we're going to have to do some work first. So the entire philosophy of statistical mechanics and thermodynamics in chemistry is finding a relationship between macroscopic properties. Macroscopic properties are big things that are averages, like a temperature, which is an average kinetic energy of all the particles in this box, or pressure, which is an average force exerted on these walls. Those are big quantities, macroscopic. The purpose of StatMech is to relate macroscopic quantities to microscopic quantities. Microscopic quantities are specific details, like how fast is this particular gas particle, atom, or molecule moving, where is it, things like that. So we need a bridge, sometimes called Boltzmann's bridge, as we'll see later, a bridge between the big and the small. So let me be a little more precise about what we mean by big and small. I'm going to define the word macrostate. So macrostate is kind of a big picture configuration of the particles. So if you have, again, this volume V and n gas particles, and there's a total energy, where energy I mean kinetic energy, just adding up the 1/2 mv squareds, or whatever. Suppose the total energy lies in some particular range. So the energy is approximately E, but you always assume in StatMech that there's some error in your measurement. So this delta just represents how precisely can we measure energy. If you prefer, say, I can measure energy in joules, but my apparatus has like some plus or minus 1% error. So this delta just tells you that the true energy can lie somewhere within our, error bounds, some sig figs or whatever. So delta itself is not actually important, but I'm just emphasizing that the macrostate has a little width, right, in energy. So anyway, this big picture quantity that says, okay, there's a total energy which is about E within our error, and a big volume V, and a big number of gas particles n, those things determine a macrostate. So the total energy is a macrostate. I want to contrast this with a microstate. So a microstate is the specific configuration of all of the particles, right? So a microstate might be if I tell you where every single one of these gas particles is, all of their locations, and all of their speeds, all of them. that would be a microstate. Now the point is that if you know the microstate, you know the macrostate, because I can always find the total energy by adding up from I equals 1 to n all of the 1/2 mv squareds, right? If I know all of the speeds, I can add up and get the total energy. So if I know the microstate, I know the macrostate. However, you can't go the other way. If I only tell you the total energy, the sum of all the 1/2 mv squareds, I don't know where all the particles are and how fast they are, because there's many different configurations that have the same total energy, right? For instance, I could take one of these particles and move it here, and then flip his direction, so he's not going up, but he's going down at the same speed. That means he has the same total energy, but it's a different microstate because I've moved that guy. So the point is that many microstates will have the same total energy and therefore correspond to the same macrostate. Okay, these are just words. We're not really doing anything sophisticated yet. I'm just defining things, but is this distinction clear?
Yes.
Good. Okay, let's try to make that a little better. Okay, so you may have heard this word equilibrium thrown around. Usually the word equilibrium means that things aren't changing in time. So when you do equilibrium in chemistry, it'll basically be something like ddt of some concentration of, I don't know, if it's an acid or something, concentration of hydronium ions is 0, or the time derivative is 0. This is what you usually mean by equilibrium in chemistry, that the concentrations of things are not changing in time, they're kind of static. We're going to be a little more precise here. So by the word equilibrium, I mean that every microstate with the allowed energy, approximately E, is equally probable. They're all equally probable. So as a simple example, just suppose we have a simple system that has maybe 2 spins. So I'll represent spins by arrows or something. So if our system has 2 spins, and it costs 0 energy for the spins to be aligned, this is a very common model, the Ising model in physics, and it costs energy E0, so it costs a higher energy if they are misaligned. So for instance, up and down. If this system is in equilibrium, and I tell you that the energy of the system is E0, then that means that the probability of being in one configuration that has energy E0, so the probability of being the first one up and the second one down, is equal to the probability of being in the other configuration, the first one down and the second one up. Why is that? Because equilibrium just means that all of the microstates with the same energy are equally probable, and we said that it's energy E0 to be misaligned. So the 2 possible states that are misaligned are equally likely. They both have probability 1/2 if we're in equilibrium. Okay, that's what equilibrium means. This silly example with the 2 spins is very easy because all of the numbers are finite, right? There's only 2 possible states with the same energy that I specified, up, down, and down, up. So here it's very easy to find what the probabilities are. For ideal gases, there aren't just 2 states. There's an infinite number of states. You can see this even with just 1 gas particle. If I have 1 gas particle, what are all of the possible states that it could be? Well, to tell you all of the information about this gas particle, I have to give you 2 pieces of information. First, the position of the gas particle, x, y, z, and second, the speed of the gas particle in the 3 directions, vx, vy, vz. And there's infinitely many choices of x, for instance, already just for x. I can pick any number between 0 and Lx, the length of the box, and I can pick any speed. If you allow this to have a sign to be, left or right, I can choose any speed between positive and negative infinity. So clearly there's infinitely many possible states for just 1 gas particle, let alone n of them. So when I talk about all microstates being equally probable in a case where there's infinitely many such states, I really mean something called a volume, a phase space volume, which I'll explain a little bit more in a moment. But all this means is that when you have something like an ideal gas, you have to do integrals to find the volume. So the total amount of volume associated with a given state that has some energy E, that thing divided by the total phase space volume is going to be the probability P of being in a state S. So this equation here is just the statement of equilibrium, that all the states are equally likely, in the case where there's infinitely many such states. So if they're all equally likely, you just find the volume associated with the state you care about, divide by the total volume, and then that's the probability of being in that state. Okay, still mostly words, but more complicated words. Thoughts on this?
I do not have any thoughts to suggest what I was internally commenting about the infinite amount of microstates.
Okay, good. But the idea is clear, that there's infinitely many of them, so we need some integral thing, right?
Yes.
Good. Okay. Onward then. Okay, now we have to do some math. So let's think about what is the total phase space for an ideal gas. So as I was signaling before, to tell you the precise microstate, so all of the locations and speeds of n particles in a box, so for an ideal gas with n particles. Now I need to give you 6n numbers. Why 6n? Because for each gas particle I have to tell you x, y, and z. So now I'm going to put a subscript I on those, where I runs from 1 to n, because there's n of these gas particles. So I have to tell you 3 coordinates for each gas particle and 3 velocities. But often in physics, rather than using velocity, where velocity, as we remember, is dx dt, it's much more convenient usually to use the momentum. Momentum is just the mass of the particle times the velocity, or m dx dt, or whatever. Maybe I should call this px or something to tell you that this is in the x direction. So this is just a stupid change. I'm just multiplying by a constant number. We assume that all these gas particles have the same mass. But that's fine. So now I need to give you 3 coordinates and 3 momenta for every gas particle. 3 plus 3 is 6. 6 times n is 6n. So the total phase space for an ideal gas has 6n numbers. Right, okay. So a simple example is if there's just one gas particle, then I have some 6-dimensional phase space where I have to give you x, y, z, px, py, pz. Okay, so now we have to figure out what the phase space volume with a given energy is. Okay, well first I have to know what the energy of a bunch of gas particles is. Well, as you've already learned in chemistry, that the kinetic energy, let me say Ke to emphasize that I mean kinetic energy of one particle is a half mv squared. We'll actually prove this in part 2 when we talk about work, because this formula right now seems like it was pulled out of my ass, but except for a moment that we will prove this later. So if I add up the kinetic energies of all n of the particles, if I add 1/2 mv squared for all, this is now the vector v squared, so vx squared plus vy squared plus vz squared. If I add up all of this, I get the total energy. And now I'm just going to change variables a little bit to go from v to p, because it's more convenient. So we know that v equals p over m, so that means v squared equals p squared over m squared. So if I plug that in for the v squared here, I have an m squared downstairs, it cancels 1m, and I'm left with 1m downstairs. So now it's just a sum of p squared over 2m. So that's the total energy. You can write it like this if you want to emphasize that there's px, py, pz for each of these guys. Now here's the key insight. This equation, well, let me write it in a slightly different way. I'm going to multiply both sides by 2m. This equation is 2me equals px1 squared plus py1 squared plus pz1 squared plus dot 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 all the way up to the nth particle, pxn squared plus pyn squared plus pzn squared. And now what we're going to do is think of the right-hand side as the coordinates in a new higher dimensional space. So for instance, if I called these coordinates just x1 up to x6n, right? This would be like x1 squared plus x2 squared plus dot 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 plus there's a total of, 3n of them, because these are just the momenta, not the positions, plus x3n squared. But we know what this equation is. You've studied this for the volumes of spheres, or balls. The equation that tells you if I add up the squares of all of my coordinates and it's equal to some number, that is the equation for a sphere in higher dimensions, right? Just like in 2 dimensions, you would say x squared plus y squared equals r squared. This is now a 3n dimensional sphere, x1 squared plus x2 squared up to x3n squared equals r squared, where r squared is 2me. So anyway, this is telling us that the phase space geometry, the shape of an ideal gas with a fixed energy is just a sphere in 3n dimensions whose radius, well, this is r squared, so I should take the square root. The radius is root 2me. Okay. Now it's getting very abstract to think about a 3n dimensional space, but try to follow the big picture. So is it clear that the equation at the bottom, this last line, is telling us some sphere in a higher dimensional space?
Whoops. But yes, that part is clear.
Okay.
Yeah, this is.
Good.
It's clear enough, the idea.
Okay. Am I distracting you from a chat?
No.
Okay. Okay. Good. Okay. Now we're going to do the actual calculation for the ideal gas law. So this thing I signaled before, that the probability being in state, is the total phase space volume in that state divided by the total phase space volume of all states. So we'd like to find the total phase space volume of this sphere with radius root 2me. We're going to cheat a little bit. Instead of finding the volume of this little sphere, we're first going to find the volume of a ball. So instead of being equal to 2me, we're going to find the volume of the ball, which contains everything with less than or equal to 2me. And then we're going to use that to get the one that we want. So first the ball with less than or equal to 2me, well, it's just an integral, a multiple integral, which you'll learn about in 1802 soon, a multiple integral with a huge number of integration variables. Dx, dy, dz for each of those 1 up to n, then dpx, dpy, dpz, all the way up to n. So it's just a huge number of integrals. But the integrals are very easy because the thing that we're integrating is just 1 with respect to all of these variables. So many of these integrals are easy to do. So all of the x, y, and z integrals are totally trivial because integral dx1, for instance, well, what are the bounds of integration that I've left out? Well, the bounds of integration over the x coordinate is just the length of the box, right? The length of the box along x goes from 0 to lx. The integral dy goes from 0 to ly, and so forth. So for each of these triples of dx, dy, dz, when we do the integral over the length of the box, we get an lx, ly, lz, which we know is the volume of the box. And then there's one of those for each of the n particles. So all of the x coordinate integrals give us a volume, and there's n of them, so we get a v to the n. That part's easy. So we get a v to the n from the coordinate integrals. What about the momentum integrals? The momentum integrals, as I just argued, if we integrate from 0 up to these momenta, that gives us the volume of a ball, volume of a 3n dimensional ball with radius root 2me. So this is the step in proving the ideal gas law where we use our results for the volume of a sphere. The volume of a ball in n dimensions with radius r is this thing, which we showed last time, or 2 times ago or something. So I'm just going to use that formula and plug it in for this volume of a 3n ball. So everywhere I see an n, I'm going to replace it by 3 times capital N. And everywhere I see a radius, I'm going to replace this by radius is root 2me, or 2me to the power 1/2. And then that gives us this result here. So where did this come from? Well, the Vn I just carried down. The pi, well, I replaced n by 3n over 2, so now it's pi to the 3n over 2. The gamma, again, I put a 3n in. And then for this radius, I just put root 2me is 2me to the power 1/2, and then by power to a power, this thing becomes 3n over 2. So it was 3n and then the 1/2 from the square root. Okay, so this is our first results for the phase space volume of the solid ball, not the sphere, of all the ideal gases up to the given momentum. Now we have to play around with this a little bit and make it look simpler. But, okay. Badoop.
I was about to say, this looks nothing like the ideal gas law.
Nope, we're not done. Not yet. The questions on this before proceeding.
No.
Badoop. Proving things is hard, man. Ideal gas law doesn't come for free. It resists. Okay. What's the next step? Okay, well, as I signaled in the preview, we're going to use Stirling's approximation. Why? Because n is huge, n is like Avogadro's number, and we have a gamma function downstairs. So we're going to assume, first of all, n is so large that 3n over 2 plus 1 is approximately the same as 3n over 2. So I'm just going to drop 1s mercilessly, just genocide every plus 1 somewhere. And then if you use Stirling's approximation, which you found before, it turns into this thing. So I put the 3n over 2 plus 1, then I kill the 1, and I put for lowercase n, I'm putting in a 3n over 2 everywhere I saw that. So in the first line, I'm just copying Stirling's approximation exactly. In going from the first line to the second line, I'm killing some of the factors of plus 1. So 2 things to be careful about. 1, I killed this factor of plus 1. The second thing is I combined these factors. This is 3n over 2 to the power 1/2 because it's in a square root. This is 3n over 2 to the power 3n over 2. So when I combine them, I get 3n over 2 to the power 3n over 2 plus 1/2, right, by product of powers, where the 1/2 again is coming from the square root term. But now since n is huge, I can ignore that 1/2, right, because 3n over 2 plus 1/2 is almost exactly the same as 3n over 2 when n is huge. So I kill that factor of 1/2. That's what gives me this thing. And I'm left with this factor of square root of 2 pi. But I'm actually going to kill that as well for the following reason, because this is a factor of 2 pi to the power 1/2. But in our formula for phi up here, we already have a factor of pi raised to a huge power, pi to the 3n over 2. So this factor of pi to the 1/2 is going to combine with this and give us a factor of pi raised to like 3n over 2 plus 1/2, but 3n over 2 plus 1/2 is almost the same as 3n over 2. So you might as well just not even include it. Same thing with this factor of 2. This is a factor of 2 to a huge power, so I'm going to drop this factor of 2 to the 1/2. So whenever you have big numbers, you just mercilessly kill anything that's not big. Anyway, so just if we do that, this is what we get after Stirling's approximation by just plugging in for this thing in the bottom and collecting like factors. Okay, and I remind you, this is not the volume we want. This is the volume of a ball, not a sphere. So this includes all the momenta up to E.
So should that still be an approximation, or at least using the approximation sign?
Yeah, I guess I should use an approximation. This is an approximate volume when n is large. Yeah. I'm going to start treating approximations as exact, though, because the ideal gas law itself is an approximation, but we write it with an equal sign.
Huh. Interesting.
Yes. Ba-doop. Doop.
Oh my god, if I could stop, I just keep bumping it.
Okay. Well, let's turn this into the volume of the sphere, not the ball, this little sphere with thickness delta that we want. And to do that, we should remember something from way back when we did tangent line approximation. So what was that? Remember, we had this problem way back when we did tangent line approximations, and I said, suppose I want to find how much volume of paint I need to paint a very thin shell, where I'm drawing it a little thicker than it should be, just to emphasize, but a very thin shell that's like maybe 1 millimeter thick around a ball of radius r. So if you want to find the volume of a very thin shell, the way you usually do it is with a tangent line approximation, because the true volume of that shell would be, of course, in 3 dimensions, 4/3 pi times the big volume, r plus 1 millimeter, cubed, minus the volume of the small ball, 4/3 pi r cubed. So this is the true volume, but if you don't want the true volume, you just want an approximation when the thickness is very small, you can use a tangent line approximation. The tangent line approximation to the difference of this function evaluated at r plus delta and this function evaluated at just r is, of course, the derivative of the function times that distance delta. So we used this way back to find the volume of this shell. We just took the derivative of the volume times the thickness. So in other words, all I'm saying here is that the volume of the shell is approximately the derivative of the volume of the ball times the thickness. Thick again. So that worked in 3 dimensions. We're going to use something identical here in 3n dimensions. So since we're trying to find the volume of a little shell with thickness delta in energy space, because remember delta is our energy resolution. So the thickness of this ball is delta, because this is going from energy now E. Remember, this is a ball in energy space. So it's going from e to e plus delta. We're going to do the same thing. We use a tangent line approximation and say the volume of the shell, which I write as capital omega, is the derivative with respect to e of the ball volume from the previous slide, times the thickness delta. And if you evaluate that, it's actually very easy to evaluate because n is so large, right? So if I take the derivative, here's the thing here. If I take the derivative of phi with respect to e, well, by the power rule, since remember e appears inside here raised to some power, by the power rule, this should really be, you pull down a factor of e to the 3n over 2, I keep that v to the n, and then I should have a factor of this thing by the chain rule, 3n over 2 minus 1, right, by the power rule, and then times some other junk from the inside. But again, since n is very large, 3n over 2 minus 1 is effectively the same as 3n over 2. So I'm just going to drop that factor of 1 again when we take the derivative. So anyway, all the derivative is going to do is pull down a factor of 3n over 2, and then some junk from the inside. And that's the volume, the phase space volume for the ideal gas. So here's the 3n over 2 outside. I multiply by this delta, and then I think there's, where did this 1 over e come from? Probably from, oh, I guess I did keep this, the minus 1. Yeah, the minus 1 up here, you could write as e to the power minus 1 downstairs. So I'll probably drop this on the next slide, but this is from the power rule, the thing I was just arguing we should drop. Then you have all this junk, but this raised to the first power again times this thing to the 3n over 2 power, you can just drop the thing on the inside. Okay, there's a long calculation, but this is the thing, the number of microstates, which will actually give us the ideal gas law shortly, after 2 small corrections, which I'll show you on the next slide. Okay, so what are those corrections? This is the volume of the ideal gas law phase space with volume E. There's 2 things we have to change, which you'll study in more detail if you take a thermo class. First I have a picture. Yeah, a picture. This is the thing I just drew a moment ago. So I took this from a textbook where they had radius E instead of radius 2me. So I guess this is m equals 1/2. But anyway, so yeah, the volume of the shell in momentum space is just roughly the derivative of the volume with respect to the radius times the thickness, which here they call delta E. So delta E is the thickness, which I was calling delta before. So this is just the visualization of the volume that we're caring about for this ideal gas. Good. Okay. So now I'm going to make 2 small corrections. The first is because our n gas particles are indistinguishable. So we've actually overcounted a little bit, right? If there were just 3 gas particles, then the count that we just did would, for instance, maybe assign, it would count this phase space state where our 3 gas particles are moving like this, but then it would have counted again another phase space state where the configuration of the gas looks the same, but we're just calling them different things. So now gas particle 2 is here, 1 is here, and 3 is here. So we've just swapped 1 and 2. Because we counted all of the states with a given total energy, including ones that just have the same positions, but we're just labeling the particles differently. So as you probably remember from, wherever you learned counting in like 6th or 7th grade counting problems like this, if these particles are indistinguishable, you shouldn't count these 2 things as genuinely different states, right? If they're indistinguishable, these guys don't actually have labels attached to them that tell you which is which. So these things are the same. And the number of ways of rearranging n particles that are indistinguishable is, of course, n factorial. So we overcounted. We should actually divide by n factorial to get the correct count. But by Stirling's approximation, again, n factorial up to this root 2 pi n, which I'm going to just drop because it's small comparatively. This n factorial is like e over n to the n or something. Well, sorry. This is, the thing that I've written here is actually 1 over n factorial, right? Because n factorial is root 2 pi n over e to the n. Ba-doop. So
but you do say you're dividing by a factor of n factorial.
Yeah, but I put n factorial approximately, so I really should have put, we're dividing by a factor of n factorial and not said that's approximately equal to this. I should have said when you divide by that, you get this factor.
Okay.
I was being a little fucky, but yeah, there's one other. Okay, so the one other very deep thing is, which I'm not going to explain why this is deep, but if this omega is just counting a number of states, when you count things, you count how many things there are. That count should not have units, right? The number 5 does not carry units. But the thing that we wrote down before, this omega, actually did have units. It had units of position times momentum, which it should not do. So we actually need to divide by something which has units of position times momentum and the appropriate number of them, actually 3n of them, because of the integrals that we did. So as it turns out, for reasons which are actually, pretty complicated to explain, the right thing to divide by to give this the right units, which are no units, is the constant h bar which comes out of quantum mechanics. And this is really fundamentally because these particles are quantum mechanical and they're indistinguishable. So this h bar appears in a way which is a bit mysterious because it seems like we're not doing quantum mechanics. But as we'll actually see, even though this thing appears in our count for the phase space volume, it's going to drop out of the ideal gas law, because the ideal gas law itself is not a quantum mechanical statement, it's just a classical statement. But anyway, that's just a very mysterious comment at this point. So anyway, final answer. This is the phase space volume associated with the ideal gas of energy E. So phase space volume of an ideal gas with energy E in a box of volume V. Looks like a terribly complicated formula, but actually this is where all of the physics of the ideal gas comes out. So all we need now is this bridge. Remember, this is counting microstates. We just need a bridge between this and a macroscopic quantity like pressure and volume in order to extract the ideal gas law, which I'll show you shortly. But first, questions on the phase space volume. Ba-doop.
This entire thing is a black box.
Good. Okay. Well, it's supposed to be more of a tour of a preview than anything, but I guess the things to keep in mind are, one, we're counting the number of ways of configuring ideal gases with total energy E, and two, we critically needed the volume of a sphere in 6n dimensions. So that's where the integral entered there, and it's Stirling's approximation, actually.
Okay.
Good. Okay, so this is our answer. Now let me show you how to get the ideal gas law out of this. So we need a definition of entropy. And this is actually a famous definition, the Boltzmann entropy. So Boltzmann actually had a very sad life. He ended up committing suicide, but he was so enamored of this formula that the equation S equals K log W, I use omega instead of W, but this is carved on Boltzmann's gravestone. This definition of entropy. So it was apparently very meaningful to him. But anyway, this is when you use entropy in chemistry, which, if you learned it in your chemistry course already, was probably defined in some shitty hand-waving way as like, entropy is how disordered something is. But that doesn't make any fucking sense. No one ever defined what it means to be ordered or disordered. The true definition of entropy is this. It is a constant, some number, the Boltzmann constant, which you can just look up. So that's just a number. It's a number times the natural logarithm of the number of microstates. K log omega. That's it. That's what entropy is. It's very, very simple. Why do people say bullshit like this has something to do with the amount of disorder? It's simply because if there are many, many microstates that correspond to the same macrostate, then it tends to be something we would think of as disordered. So for instance, if there's something which is a perfect crystal, perfectly ordered, where you just have all n of your atoms that are all, say, equally spaced, they have the same distance a between all of them, and they're all sitting perfectly still, so all of their velocities are 0, this is perfectly ordered, right? How many microstates are there that are associated with this perfectly ordered macrostate? Well, there's only one. Right? There's nothing to integrate over. We can't integrate over different positions for all of these particles because I've told you that they are all separated by the same distance a. So there's no choices to make in the positions. Do we integrate over the different speeds? No, because I told you they're all sitting perfectly still. V equals 0. So there's no velocities to integrate over. So that means there's only one possible microstate for a perfect crystal to have that macrostate. And therefore the entropy of this state is proportional to log of 1, which is 0. So this highly, highly ordered state has 0 entropy. On the other hand, if we have an ideal gas where you have a huge number of particles that are all over the fucking place, and all you know is the total energy, how many different microstates are there with that total energy? Well, as we just calculated, there's a fuck ton of them, right? Because all of these guys can be in infinitely many positions. They all have some speeds, but I can move them around and change their speeds in such a way that the energy stays the same. So there's many, many microstates associated with this same macrostate, and therefore the entropy, which is the log of a huge fucking number of microstates, is going to be pretty big. So this is why people say that, entropy is measuring disorder, because this seemingly disordered collection of particles has a large number of microstates associated with the same macrostate, and therefore a huge fucking entropy. The crystal had only one microstate for its macrostate, so it had 0 entropy, which seems highly ordered. But anyway, saying entropy is disorder just it confuses people, because it's not what it is. It's the log of the number of microstates. That's what it means. You can say poetry and say words about it if you want after you've defined it, but you have to fucking define it first. All right, so fine, let's compute it. What'd you say?
Did you not attend high?
Wait, sorry, you're laughing. What did you say?
Did you not attend highs? That they never tell you about what things actually are.
Now the connection's back. Sorry, I heard.
Is this working?
Yeah, can you hear me?
Yeah.
Okay. Can you repeat that sentence again? Sorry.
Summary is high school never tells you why or what something actually is.
Yes, it's true. It's really frustrating, though. I hope you're frustrated by this, because you're not learning anything. If someone stands in front of you and said entropy is disorder, and then they show you some fucking picture of like a bunch of cards, and like you throw playing cards all over the table, and they say, look, it's disorder, this has high entropy. It's like, what the fuck does that mean? You can't do math if someone just tells you, entropy is disorder. It doesn't. You make no predictions. It's not even science. It's just words. But anyway, frustrates me. But I'm trying to fix that. So now we actually know what entropy is. It's k times the log of the number of microstates. So let's just log this fucker. The nice thing about log is that log of a product is going to break into sum of logs. So I'm going to add up the logs of each of these things here separately. And the other nice thing about logs is that log of a power comes down into a coefficient. So log of things raised to the n power, I'm going to pull all of these n's out. This 3n over 2 is going to come out. This 3n over 2 is going to come out. These are all going to come out as prefactors. So let me write that down on the next slide. So when I pull out all those prefactors, here's the n out front. Now I got this log v over n from the first term, right? This guy here, this v over n, came from the log of the first term. Then I had this 3 halves that came from pulling down the 3 halves, and I've already factored out the n, right? So I've already factored out the n, and there's a 3 halves left in front of the energy. So you might have heard this before, that the energy of an ideal gas is like 3 halves nkt or something. That's where the 3 halves is where that came from. But that's not what we're talking about today. We're talking about the ideal gas law. So that's the second term. The third term I don't give a fuck about for the following reason, because the third term, this guy here, actually also the e, actually also this basically, because this thing is like e to the power minus 1, but we already have a big n up here, so I can kill that minus 1. Anyway, everything the rest is constants, right? E, this is just, Euler's number E. M is the mass, 3 pi h bar, this is just a number. And we're going to end up taking derivatives of this. So everything else is a constant, and it's actually going to go away when we take derivatives. So anyway, I'm just going to write it as const. So good. So this is actually an incredibly important formula. This is the entropy of an ideal gas with energy E. And now this is the Boltzmann bridge. This is the connection between microstates and macrostates, and just where all of the money shots are going to come from. Because for all that work that we just did, computing the number of microstates associated with the macrostate, now we can use thermodynamics to turn those into macroscopic statements. And this is where I'm going to have to cheat a little bit and cite some results that haven't been proven to you yet. But one of those results is something called the first law of thermodynamics, which you may have actually learned about in chemistry, although it was probably just told to you and not justified. But anyway, the first law of thermodynamics is usually written like this in terms of these, exact differentials, as they're sometimes called. So, as we say in calculus, dv dt isn't a ratio of things. It's just a derivative. But it's actually possible to define these d's in a precise way as differentials. So if you don't want to think about it that way, you can just think of these as finite deltas. So the change in energy, if you will, is the temperature times the change in entropy minus the pressure times the change in volume. So if you like, just think about this as the statement of energy conservation. If you change the energy a little bit, that energy either goes into temperature or it goes into changing the volume, or both. Anyway, so that's the first law. Okay, so now we're going to use the first law to get an equation for the pressure. And I'll ask you to do that as a challenge, actually. So, all right, so I'm going to ask you to do some sketchy math, but that's all right. We'll do it anyway.
I can't do normal math, right?
Well, sketchy math is easier than normal math because you don't have to be rigorous. But okay, so good. We're going to start with this. This is the first law of thermodynamics. We're going to say the energy of the gas isn't changing, so du equals 0. So in other words, that's T ds minus P dV, all equals 0. And I'm going to ask you to turn this into an equation for a derivative of the entropy. So the first thing I'd like you to do is, how do I take this equation pretending that these ds and dv's are actually like small changes, delta s and delta v? Pretending that, how can I divide this by something and take a particular limit which will give me an equation for pressure in terms of a derivative? What should I do?
All right, so we follow the hint and divide each side by dv.
Okay, what do I get?
So 0 equals TDS minus PdV over dv.
Yeah. So,
or I don't know if dv can be divided out.
Yeah, it actually can. So, so you can actually cancel this. Okay. All right. So now if I take a limit as dv goes to 0, this thing actually turns into a derivative, right? So, so doing that, what equation do I get for the pressure?
So let's see. Trying to understand what you mean.
Yeah, it's a simple thing. I'm just saying move the pressure to the other side and say that,
oh my god,
this thing becomes the
so
derivative of the entropy.
Pressure equals T. Yep.
Yeah, okay. Good. So this was hacky, but you can actually do this in a careful way if you want. But it's, I mean, if you do it the careful way, you get the same answer. So this is correct. Pressure is temperature times the derivative of entropy with respect to volume. But lucky us, we have an equation for the entropy right here. So next thing, take a derivative of this to tell me what is the derivative of entropy with respect to volume.
So ds ev, okay. Let me think. Well, k sub e and begin brackets. Begin parentheses. N over v plus 3, well, n over v plus 0 plus 0.
Wait, do this again. So derivative of log is 1 over the thing, so that was n over v, but then times the derivative of the inside. What's the derivative of the inside?
The derivative of the inside is v.
Rotating.
No, 1 over... The derivative of the inside is 1 over n.
Okay, so by the chain rule I should do this, right? And then plus 0
yes.
plus 0, you said?
Yep.
Okay, so that's...
So equals kbn squared.
Well, no.
No, kbn over v.
Good, okay. Plug that in here, and what do I get?
D equals tv.
Wait, what? So...
P equals kbn over v. T times kbn over v. There we go, finally.
Good. T times kbn over v, or multiplying both sides by v, you can write this as pressure times volume is the Boltzmann constant kb times n times t. So this is the ideal gas law written in physics notation. The difference between physics notation and chemistry notation is here n is the number of gas particles, right? Usually when you write the ideal gas law in chemistry, You don't say this is the number of gas particles like atoms or molecules, you say this is the number of moles. So if you change this from the number...
I mean, they are effectively interchangeable.
Yeah, they're effectively interchangeable. It just changes this number, right? If I multiply this by Avogadro's number, then I'm going to, go from the chemist to the physicist version, basically, right?
Yeah.
So they're the same. Okay, good. So we've actually, I shouldn't say derived because I cheated and used some results I haven't proven, but I have sketched a caricature of the proof of the ideal gas law. We had to count a number of microstates, then use the Boltzmann bridge, S equals K log omega, and then use the first law of thermodynamics that tells you how pressure is related to entropy. And this gave us PV equals NKBT, which is not bad from scratch, effectively scratch, to prove this ideal gas law. So I think it's very important just to remember the ingredients that went into this, because we never had to go do an experiment. This had nothing to do with actually going into a lab and measuring pressures and temperatures. All we had to do was assume that you have some box made out of little particles moving around with certain speeds, then do some integrals involving the volumes of spheres and high numbers of dimensions, and then use some laws of thermodynamics, and it told you the relationship between pressure, volume, and temperature. So in particular, nothing in any of these steps required us to know what the balls are made of, right? Like whether they are atoms or molecules or tiny, tightly wound strings or whatever. Nothing required knowing the identity of the particles. Nothing required knowing their masses. The masses are not relevant for the ideal gas law. All of that dropped out. So the ideal gas law is actually a very general mathematical fact that's just true about little balls bouncing around in boxes, not just for real gases in the lab. So it's math, basically. Good. Okay, this is just the same thing that you just told me. Yeah, if you divide out by dV, the first law becomes P equals TdS dV. Take the derivative with respect to V of entropy. These guys die. You're left with KBN over V. Set that equal to P over T, and you get PV equals NKBT, which is what we wanted to show. Okay, confusing, long calculation, but I think it's good for the soul to know that the ideal gas law can be proven. So, thoughts, questions, concerns, or death threats about that? Ba-doop.
Nope.
Ba-doop. Okay. I'm just having too much fun. All right, so let's do something else. Another application of integrals. So yeah, I cited this result with that proof that there's this thing called kinetic energy that's a half mv squared, and this was probably also fed to you, in previous science courses in high school, and I know it also appeared in your 3091 course at least once, where you're computing energies of things. So you're probably thinking, where the hell does this come from, and why is it meaningful? And again, just like the ideal gas law, this isn't some God-given formula that someone handed down to you. This just pops out if you write down, the equations of motion from Newton's laws and do some math. This thing is going to appear in a very natural way. So we're going to see that next. Good. So first I want to review some basic physics that we had before. So a long time ago, when we were talking about applications of derivatives, I told you Newton's second law. So the high school version is F equals ma. That's what people are normally told. But you should remember acceleration means the second derivative of position with respect to time. So d squared x dt squared. Or if you prefer, you can say that's the first derivative of velocity, F equals m dv dt. All of these are equivalent ways of writing the second law. So example, we've done this problem many times. If you are dropping some object of mass m and it feels a force mg downwards, then F equals ma becomes, the F is minus mg if it's going downwards, equals ma. What is a? It's d squared. Maybe I use the letter y for the height, dt squared. I cancel the m's. I take an integral on both sides. So I integrate both of these to get rid of one of the derivatives. Now I have minus gt plus a constant. What's the constant? Well, it should really be the initial velocity in the y direction. That thing is dy dt. Now I take another integral with respect to t. By the power rule here, I get a minus 1/2 gt squared. By the power rule here, I pick up a factor of t plus v y0 t. And then I have another constant, which is maybe y0 equals y. So that's how we use Newton's law to find how something behaves when you drop it or throw it. drop it from some initial height y0, maybe you give it some initial speed downwards, v0y or whatever, and you get this equation for the height as a function of time. And you did very, more sophisticated examples of this with like a projectile where there's an x and a y part and all this other junk. All right, so we know how this works. The whole name of this game was to write down Newton's second law and take integrals with respect to time to kill off these time derivatives. But you might have asked, okay, is there more? What if instead of integrating with respect to time, I did something a little more clever and integrated with respect to x, for instance? Would that give me something interesting, or would it give me total nonsense? We'll see, it actually does give you something interesting. So let's try and see what happens. What happens if we start with Newton's law? Now I'm going to put in this x in parentheses to remind us that the force can now depend on x. For instance, the most perhaps familiar example for you is, now that you're doing electrostatics, if you have some big charge q, the force certainly depends on where you are in space because it goes like 1 over r squared, where r is your distance from the charge. So the force can depend on your location. So I just put an f of x to indicate that. Okay, so f of x is m dv dt. This is one of the ways of writing acceleration. And now we're just going to integrate both sides, not over time, but over x. So on the left side, it's just an integral from some starting point xa to some ending point xb of f of x with respect to x. And on the right side, mass is a constant, which I will pull out. We have an integral again from xa up to xb of dv dt with respect to x. Okay, so it looks like this hasn't done anything for us. It just got more complicated. If we know what the force function is, how f of x depends on x, then the left side is just some number that we could compute. The tricky part is handling the right side. Is there some way to manipulate this and massage it into something which is more useful? And there is, and you're going to tell me how to do it, in fact. So we're going to start with that integral, the same one, m integral from xa to xb of dv dt. You're going to make a u substitution. So we're going to change variables from x back to time. What do I mean by that? We mean x is a function of time. X equals x of t. So we can make a u substitution where if I just hit both sides with the d, dx is dx dt dt. This is just like the usual u sub, except I'm using the letter u instead of x. So make that substitution and plug it into this integral, and then evaluate the resulting integral. You'll just, there won't be an integral left. You'll just get some answer. So, okay, first of all, what do I do when to get the u sub done?
So you've given me x and dx.
Yeah.
Okay, so let's see. There are no other occurrences of x in the integral already, so we simply have to substitute dx.
Good. What does that give me?
M from xa to xb of dv dt times dx dt dt.
Dx dt dt. One thing is the bounds are going to change. It's no longer from xa to xb, because now we're integrating with respect to t. I haven't told you what the endpoint should be.
X of a and x of b, I guess?
Well, let's just call them ta. Oh, why did that get thicker?
Thick.
Yeah. Let's just call them ta and tb for convenience, where what we really mean is x evaluated at the time ta is the same as xa, and x at tb is the same as xb. It's just easier. Okay. Well, we have a different name for dx dt. What is dx dt also known as?
Let's see. dx dt. Inhale.
What is it? What is this? Is defined as a different letter. What is it?
It's dx divided by t. It's itself. Okay, of course. Did this show up in the prior slide?
Probably. Yeah, way back here. Yeah, we just have to remember what x, v, and a are, right? The derivative of x with respect to time is v, the derivative of v with respect to time is a, so we should replace dx dt with what?
V?
Yeah, this is just v. So now there's a trick for evaluating this integral. You could do it in two ways. You could either integrate by parts and relate it to itself, because you could see we have something v and its derivative, dv dt. So one thing you could do is move a derivative onto this guy and see, oh, that's going to be the same thing. Another thing you could do, which I prefer because this trick comes up over and over again in physics, is to notice that this thing is the same as the integral from ta to tb of 1/2 times the derivative of v squared. Okay, so I'll ask you to explain to me, why is it that 1/2 times the time derivative of v squared is the same as dv dt times v?
Okay, so I guess let's work backwards. So take d dt of v squared.
Yeah. What do you get when you do
So
that?
d dt v squared is equal to 2v times dv dt.
Good. And then what?
And then the 2v cancels with the 1/2.
Yeah.
And we get the first.
Good, exactly. So when the ddt hits this thing, the power rule brings down a 2, which kills this 1/2, and then I get v dv dt, which is exactly the same thing up here. So yeah, this is true. This comes up very frequently, that you have an integral of a thing times its derivative, and you usually want to replace it by the derivative of the square, right? Because just d dt of v squared is 2v dv dt, and you correct the 1/2. But okay, now this I claim is a stupid easy integral to do by the fundamental theorem of calculus. So using FTC, what does this integral turn into?
Let's see. Oh. I don't see.
It's an integral of a
Anything.
derivative. What is the fundamental theorem of calculus?
Crap! It's going to be 1/2 v squared, or at least
Yes.
the antiderivative.
Yeah, we still have the 1/2 m outside, but then, yeah, so the integral of d dt v squared is v squared, but we still have to evaluate at the endpoints, right?
So, TBTA.
Yeah. Okay, and we might as well invent some new notation. Why don't we just say that the velocity at the time tb is vb, and the velocity at the time ta is va, so then this thing is 1/2 m vb squared minus 1/2 m va squared. Good. Are you happy with that?
Yes.
Okay. Let's just see it again in LaTeX. So good. When you make this fairly obvious substitution with dx, this thing, the dx turns into dx dt dt. So dx dt is simply v. So we have a v dt here. As you pointed out, if I take the time derivative of v squared, I get 2v dv dt. So if I divide by 2, that just gives me back v dv dt, which is the original integrand. And then by the fundamental theorem of calculus, it's just always true that, integral of d dt f with respect to t is simply f, right? I mean, the integral kills this derivative. That's just what the fundamental theorem tells us. So this thing, since we have a definite integral, it's really just v squared evaluated at the endpoints once you pull out the 1/2. And then that's the same as 1/2 mvb squared minus 1/2 mva squared. But these expressions are probably pretty familiar from the kinetic energy. This 1/2 mv squared is a pretty important number. Let's just remember where this thing appeared, the original equation, the context where we were evaluating these integrals. Remember, we had an equation with an integral of f dx on the left side, way back here. Integral of f dx is m integral of dv dt dx, and we just evaluated the right side and found that it's basically the change in 1/2 mv squared. So this is something which is often called in physics the work-energy theorem. What does it tell us? It tells us that if you integrate the force over a distance, integral of force over a distance, which is a number called the work, that gives you a change in kinetic energy, so change in kinetic energy where we have defined a quantity called the kinetic energy, which is a half mv squared. So again, there was no fucking magic here. It's not like we pulled a half mv squared out of a hat. It's just we had this question of what happens if you integrate Newton's law over space. We just did some math, and this 1/2 mv squared came out on the right-hand side. And what the equation tells us is that if you apply a force over a distance, it will cause a change in this quantity called the kinetic energy. So in cartoon form, where all of the integrals are hidden, this is sometimes written as W sub BA, which means the work done between a final point B and initial point A is KB, the kinetic energy at B, minus KA, the kinetic energy at A. So doing work leads to a change in kinetic energy. That's the theorem. It's no magic, it's just an integral. Okay, questions on that before a challenge that will give you an example?
I do not have any questions. I was going to say, oh wait, this is the work energy theorem. I thought we were going to be working all the way up to the kinetic energy.
Yeah, this is it. The kinetic energy appears in trying to prove the work energy theorem. Right, good.
Yes.
Excellent. Okay, let's do an example. So, classic example is spring. Probably the most common example in all of physics, because quantum field theory is really just about springs. Okay, so we have a mass m, capital M, in kilograms or whatever, and you attach it to a spring. The spring has an equilibrium position where it's happy. If you set it at the equilibrium position, it just doesn't move. That's where it sits still. So we're going to define that to be x equals 0 is the equilibrium line. We assume that if you pull this spring away from the equilibrium, so if you stretch it, obviously if you stretch a spring, the way springs work is that this spring now wants to pull the mass backwards towards its equilibrium position, because that's what we mean by spring. So we'll assume that the specific expression for that force is F equals minus kx, where k is a number that just describes the stiffness of the spring. It's called the spring constant. Why is it negative? Because if x is positive, which means we have moved the spring to the right, then the force wants to pull it back to the left. And similarly, if we compress the spring, so we move x to the left, so x is negative, the spring wants to push this guy back out, so the force should be positive. Right, so the minus sign just tells you the force pushes opposite the displacement. All right, fine, no magic here. But now let's use our formula that integral of f of x dx is the change in the kinetic energy. Suppose the spring moves from an initial position x0 to a final position x. I'd like you to find the change in the kinetic energy, which is the right side of this equation, by integrating the force. So what happens if I integrate the force between x0 and x?
So we are going to be integrating over from x0 to x of f of x dx, where f of x equals negative kx.
Yeah, good. So this is minus kx dx. Good. What's this?
And that is equal to 1/2, well, 1/2 negative k x squared. Of course, the x squared is in brackets. Big boys.
Yeah. Okay. And then when do I evaluate, what do I get?
So 1/2 kx squared minus 1/2 k sub 0 to the power of 2 squared. To the power of 2.
Yeah, there's an overall minus, so I'm going to move that in because in here it's x squared minus x0 squared, but when I move in the minus sign, that means the first guy's negative and the second guy's positive, because 2 minuses make a plus. But yeah, that's fine. Yeah, so indeed, it's minus 1/2 kx squared plus 1/2 kx0 squared. Good, so that's fine. That's the work done in moving the spring. That should be a lowercase, whoops. Moving the spring from x0 to x. Indeed, you just integrate minus kx from x0 to x, and you get this expression minus 1/2 kx squared plus 1/2 kx0 squared. So notice this, again, the work is negative if this guy is larger than this guy, because the first term is negative, as it should be, because the work is the change in kinetic energy. So if this guy is moving with some speed and then he stretches to some larger displacement, he has to lose speed in order to stretch. and it's positive if it's the other way. So if he goes from moving very slowly at a large displacement and then moves back towards equilibrium, the work will be positive and he's moving faster. Okay, fine. I mean, this was a simple exercise, but now we should see a more complicated exercise. How do we use this to actually solve for the motion of the spring at all times? So now a more complicated example, which already has a typo. Oh wait, no, that's not a typo. That's correct. Okay. Okay, so we're going to release the spring from rest. So here's x equals 0, and we're going to release the spring. We're going to basically hold and stretch the spring to some larger position x0, and then we're going to let it go. So if I stretch the spring to here and let it go, we expect it's going to oscillate back and forth, right? It's going to start moving back this way, and then it's going to do this again, and it's going to oscillate. We're going to try to prove that, though. So what you just told me is that if the spring goes between a position x and a position x0, the right side is the change in his kinetic energy. But we know the change in the kinetic energy is a half mv squared. It starts at 0 speed, right? v0 equals 0. So on the left side, we have a half mv squared minus a half m times the initial speed, which is 0, quantity squared. So that goes away. This term is 0. And now we're going to try to find v as a function of time, and then integrate with respect to time to get x as a function of time. So we'll do it in a couple steps. So first, step A, the easy equation, or the easy step. When this 0 squared goes away, what happens if I solve this equation for v?
You multiply the right side by 2 and divide it by m.
Yeah.
And then, well,
then take square root.
And then you take, yeah, and then take the square root. So v equals 2, begin parentheses, negative kx squared plus kx sub 0 squared over m and all of that stuff in the square root.
Yeah, how should I write that? Maybe I'll put the 2 over m out here, and then I'll put it all in the square root. Okay. Okay. Let's see if we can simplify this a little bit. So this looks like root. How can I do this? Yeah, maybe I'll just do this. So this is root 2k over m times root x0 squared minus x squared. Is that all right? Because I can pull out the k and put this 2k over m outside. Is that right?
Sounds right.
Okay, so that looks good. So that's v of t. We remember v is dx dt. Okay, so let's, yeah, that's probably the best way to write it. Okay, so we've done part A, basically. Now we want to take an integral to find x as a function of time. So if we want to integrate this, it's actually more convenient, and this is kind of hacky, but what we really want to do is what we call separate variables, which we'll describe more when we talk about differential equations. But what we should really do is think of this as dividing both sides by this expression, which involves x, because we want to integrate a function of x, which means we want to get all the x's on one side. So I'm going to rewrite this as dx dt times 1 over square root x0 squared minus x squared equals root 2k over m. And now I want to integrate both sides with respect to time. So integrate both sides dt. So when I integrate both sides with respect to time, do you see what's going to happen on both sides when I integrate dt?
So on the left side, I believe we're going to have integral x times the integral 1 over root x squared 0 minus x squared.
Yeah, so this is going to be, yeah, you can either see that by the hacky thing of like canceling the dt's or whatever, pretending it's a fraction, or you can, I don't want that, I want this, or you can just do a u substitution to the x variables, which then, as you said, means this turns into the integral of dx over this thing. What happens when I integrate dt on the right side?
Is going to become well, on the right side is going to become root 2k over mt.
Good. So this should be root 2k over mt. Okay. Now, can you evaluate the integral on the left side, perhaps using a hint?
Yes, the hint. Let's see. Let's trig sub x equals root x0 times x.
X equals root...
root x0 times u.
X equals root x0 u. Okay, so then x squared is x0 u squared? Is that what you want?
I don't believe that's what I want.
Okay.
So let's get rid of the square root.
Okay, how do we get rid of... Well, I mean, we could either just go through the steps of the trig sub, or we can just use the hint. Because the hint tells us what this integral is.
I mean, I wanted to go through the arcsine jazz and show that we can pull out the stuff, but...
Okay, I can... well, I'll do that if you want. If you want to do that, then what we have to do is the following.
It is equal to arcsine of x over x0.
Yeah, okay, so that's fine. Well, now I want to do it. So it's actually 1 over x0 integral dx over root 1 minus x over x0 quantity squared. Then you u sub x over x0 to get rid of this x over x0. Then you do x equals sine theta. So this is 1 minus sine squared theta, which is cos theta. And the dx becomes a cos theta d theta. And then you integrate this thing, which has a cos theta over cos theta, which is just integral d theta, which is theta. And then you solve this thing for theta in terms of x, which is arcsine x. So at the end of the day, well, arcsine x over x0 because we u sub. So that's how you prove it, that it's arcsine. You have to factor out this thing and then do the trig sub. Well, that's fine though, because we spent a whole chapter doing that. So that means basically arcsine of x over x0 equals root 2k over mt. I now see that I made a mistake because I copied the thing from the previous slide wrong, because on the previous slide we found 1/2 kx squared, not kx squared. But you will notice on this side I have lost the factor of 1/2. So all of these 1/2s were supposed to be there in the first step, but then when all of those 1/2s were present, we could have just multiplied both sides by 2, which would have killed all of the 1/2s. The upshot of that story is that the factor of 2 in this root k over m, which we've been carrying around, should not have been there, because I should have had 1/2 on the right side. But...
Whoa.
Yeah, anyway. Alright, so last step. In physics, it's common to define this thing called omega, the frequency for convenience, which is root k over m. So can you solve this equation for x as a function of time? Ignore what I said because it's wrong. Solve this for x as a function of time to tell me what the spring does.
So arcsine of x over x0 equals omega t.
Yeah, good. Then how do I solve?
We take sine of each side and multiply the right side by x0. So x equals x0 times arcsine omega t.
Not arcsine.
I mean sine omega t, sorry.
Yeah, good. X0 sine omega t. Have I made a mistake? I do think it's supposed to be cosine. What's wrong here? This can't be right, because this means at time 0, when we plug in the 0 on the right side, we get sine of 0, which is 0. So this should have actually been cosine, which means I made a mistake somewhere. Is this actually arcsine? I probably copied this integral wrong. Wolfram alpha. This will be very embarrassing if I did this wrong. Integrate 1 over square root a squared minus x squared. If this is arccosine instead of arcsine, I'm going to be angry. Arctangent? That can't be right. What did I...
Are you sure that you read that Wolfram right?
1 over root a squared... Oh. because this thing's all fucky now. Because I don't want that thing inside. I want this to be. Hold on. Inverse trig derivatives. Why am I forgetting? I'm going to blame this on having a cold, but why am I forgetting what the derivatives of arc sine and arc cos?
That's cos.
1 minus.
Yep.
What?
I'm confused. Sorry. Yeah, it's.
Is it the same except for this? Oh! I did something stupid. Yeah, we forgot. Yeah, it could be. I mean, it's arc sine or arc cosine, so we have a choice. But there's an initial condition because we know that at the initial time. Yeah. So anyway, when we did this integral from what were the things we were integrating from t0 up to t? Whenever you do an integral, you have an initial condition which tells you what is the function doing at the lower endpoint. So I really should have chosen arc cosine instead of arc sine, I think, when I was doing this, because we could have done the same thing and done the trig substitution with x being cosine theta. Then this would have been 1 minus cos squared, which is sine, and these things would have canceled with a minus sign upstairs. Okay, so that's what I should have done. I apologize. So I really wanted this to be arc cosine, and I wanted this to be x0 cosine of omega t. That's the function I want for the following reason, because what we expect to happen is that at time 0, this thing should be x0 when we hold the spring and let it go, and then it's supposed to oscillate the way the cosine does, because the mass on the spring goes to equilibrium, then it keeps going and overshoots, and then it goes negative, and then it comes back and hits equilibrium and overshoots again and goes positive, and it oscillates forever with some frequency omega, which is roughly, the wavelength is 2 pi over omega or something. Good. I don't think I even wrote a solution for that one, did I?
Yeah, one more. Nope. Okay.
One more. Or we could go over here and see what I did wrong, where I copied this from. Arc sine.
Yoink.
Yeah, here's the error I made. So I stole this from my freshman physics book. But again, here's, I forgot the initial condition. Whenever you evaluate an integral from x0 up to x, you have to subtract what it is at the bottom. I forgot to subtract arc sine of 1, which would have given us a pi over 2. So I really should have had a sine omega t plus pi over 2 inside, which would have given us a cosine by the usual shift formula for sine. Okay, so I fucked up. You could either do it with the arc sine and then keep the lower endpoint, or I could have done the trig sub with the cosine, and then it would have had no lower endpoint, and we would have gotten this answer. Good. Either way, this is correct. It should be a cosine. Okay, nice. One thing to conclude, so I've introduced now work and energy in the way that it's usually taught in a freshman physics class for physics majors, which is to say you integrate Newton's equations and find this conserved quantity. If you open a high school calculus textbook, it's usually taught in a very different way, which looks like this. You have a section on work where they say some words at you, like intuitively a work is, a push or a pull through some distance. I don't really know what that means. Then they just write down this equation, work equals force times distance, without telling you why. They just say that, if the force is constant, we're going to call this thing work, which is the product of force and distance.
Wait, this is a calculus book. Why are they going over physics?
Yeah, I mean, physics is just calculus with flavor.
True.
But so they write this down, and then they tell you this idea that, okay, what happens now if the force is no longer constant, right? Because this shitty definition of work, which is just telling you work equals force times distance, is only true when the force is a constant. So then they say, okay, what happens if the force is now changing? So we have some force function, here's force as a function of x. How am I supposed to compute the work when the force function is changing? Well, they're going to tell you to do the usual thing, where you break up the force function into little chunks, where it's approximately constant on each chunk, and then you say, okay, on this chunk, the work in the ith piece is approximately the force at this xi. So here's force at xi. They're going to tell you the work is approximately the force at the xi times the distance delta x or something, and then they're going to tell you now take the limit as the delta x's get very small, or equivalently as the number of intervals goes to infinity, And we showed a long time ago that this Riemann integral with a limit as the partition gets very small is the same as the definition of the Darboux integral. So it becomes an integral from a to b of f of x dx. I don't like this because it seems to me very irresponsible and out of nowhere to just write down work equals force times distance and then say we're going to turn this into an integral. That seems very out of left field. I prefer to discover it in a very natural way by starting with Newton's second law and then asking what happens as you integrate, and it just pops out that there's this quantity 1/2 mv squared, which is the thing that changes when you integrate a force over a distance. So, I don't know. You can use whichever of these you prefer, but this is the AP calculus way of doing it, and the other one is the freshman physics way of doing it. Good. All right. Wanted to have some other comments, but I guess I'll put them into the slides for next Tuesday. So, thoughts or questions on work and forces and the work energy theorem?
I do not have any thoughts, comments, questions, or concern.
Okay. Good. Okay, well, short meeting today. It's only 90 minutes instead of 2 hours, but maybe that's not.
I just had a random remembering.
What was the random remembering?
On the way back from Scotland,